All right, get out your homework.
No, I'm just disgusted. There's a pig in the classroom. Oh my god.
What is that all about?
Don't worry about it.
We're not talking about a person, are we?
No.
Yes, I am.
No.
Let's use our words carefully. All right, questions on the homework? Micah made the statement yesterday that the proofs we did in class were way harder than proofs for homework. True or false? All right, good. So, Matt, your question is on number? So, I don't know, I was reviewing some things, and that is true on these. Notice there was absolutely no creative thought process required. They gave you all the statements, you just had to come up with the reasons.
That's what I said.
So pick one and open your book so we can talk about it. Hey, let's do number one, Matt. Number one should be the easiest one, right? All right. Number one, the first step says the triangle RNX is congruent to LOY. Why is RNX congruent to LOY? Do you not see that one side of that both triangles has 2 tick marks, one side has 3, and one side has 1. That's SS. So why is angle X congruent to angle Y? It's the same, I don't know, what number am I on now? 10, 11, right? Times that we have done this, it's that same thing. Show the 2 things are congruent, show that they're part of 2 different triangles, and then show that the 2 triangles are congruent, we just did, and then you just simply claim CP. And then the last step, well, now we're showing again the 2 triangles are congruent. So NEX and OSY. NEX. I want you to look at NEX. NEX, and now look at OSY. We just claimed that angle X is congruent to angle Y. For me, I would have been putting a light pencil mark in my book, and now you can see that it's that. Why is the Y triangle NEX congruent to OSY? There's no S. NE we never showed was congruent to OS. If you put that light SAS, that's the light little arc there you put for X and Y. And then lastly, why is NE congruent to OS, therefore? How do all proofs in high school tend to end? There's number 12, right? I'm not belittling you and saying that, hey, whoa, why couldn't you get that? But I'm just going to say, recognize what's going on, right? It's like it's the same proof over and over and over again. I guess the point there is to get you used to doing that because the rest of the book is like this. I don't mean like literally every proof, but so many times in almost every proof, you show that there's some triangles, you show that the triangles are congruent, you claim CP. And it might not be how all proofs end, but it's certainly how that part ends. All right. If no questions other than that, then I will collect them. It's Friday. So I will collect them and we will do the last lesson chapter.
Very smart.
Yes. You don't need to speak interrupt in the class.
So
Ask the gentleman question.
Oh, almost. Yeah, your iris.
But dad jokes.
Thank you. All right. Let's see. 3-day weekend. Chapter test on Tuesday. Review on Monday. There's your homework. We get two theorems today. They're a little strange, right? Sometimes it takes a while to use them to get comfortable with them. They're not used too often, but we will definitely use them more than this one chapter throughout the book. I know there's one that we get later on in the book, and I always forget it's this theorem, and I can never remember what it is, the number-wise. I'm like, all right, somebody look at chapter 4. I know it's from chapter 4. You guys remember when we did the segment addition postulate and the angle addition postulate, and the two are basically the same thing, just one applies to angles, one applies to segments? Those are the two theorems we're going to get today. One's going to apply to segments, one's going to apply to angles. But they're basically the same theorem.
Oh, okay.
All right. We truly get 4 today, but 2 of them are converses, so it's got the same flavor. All right, this is a tough class because it's got a lot of new vocabulary. None of you know what a median is. You may have heard the word altitude if you had me, because I use it in my pre-algebra class. Okay, maybe perpendicular bisectors make sense, but the combination of all 4 of those today is, yeah, it's a high school class. You wouldn't want to do this to a pre-algebra class. All right, here we go. You're going to get lost if you don't take notes, right? You're not going to get this. It's just too many new words. So take great notes. First one we'll start with is this. Well, that's a triangle, obviously. If I select any one of the 3 vertices, I'll just select B at random, and I draw a line from B, from the vertex B, to the opposite side, and I'm going to pick a specific spot. I'm going to pick the middle, right? So I go from B to the middle of AC. I've made something, and in math we give it a name. It's not a bisector. It's called a median. So, I screwed this up. I should have reviewed my slides better. Okay, these are not the words you're looking for. Let's start with A. I go from A to the middle of BC, right? So therefore I cut BC in half. That red line that I just made there, we give a name. So when you go from a vertex of a triangle to the middle of the opposite side, we call this thing a median. It should be yellow, but I was lazy. It's the first hard word, and I will just say this. I gave you room in the box, and last night I was thinking, well, maybe it needs to go in the book of truth, right? I'll let you pick which one you want to put it in. But I'm going to say, we're going to use the word median a lot. Hey, make a median. If you can't remember that the median goes to the middle, M median, M middle, right? You're going to be in trouble, because we're also going to have this thing called an altitude, and it's different. It's going to say make a median, or it's going to say make an altitude, or it's going to say look at the median or look at the altitude. You got to know the difference between a median and an altitude. Medians go to the middle, MM. Now, did I say pick a specific vertex on the triangle? So how many medians do you have to a triangle? Tonight for homework, or over the weekend for the homework, we're going to see this again. I forget what the chapter is, but they're going to have you, I think it's one of the last ones you do for homework. They're going to have you make all the medians on one triangle. You're going to say, draw a triangle and then draw all 3 medians, and then tell me something. Are you listening? They're going to intersect. And you're going to say where they intersect. And then about 4 chapters from now, we're going to come back to this idea that the medians all intersect. And then we get these really ugly theorems from it. Oh boy. And we get formulas with it as well too. But we'll talk about that when we get to that chapter. Okay, so median, pretty easy. Now remember, it can be any one of the 3 vertices, right? So if I made it from B, it would look like that. If I made it from C, it would look like that. The key here is that the median takes the opposite side and cuts it in half. That's really the key. Who's lost? If that's all it was, this would be easy. And it's not, it's more. Okay? All right, so different idea, right? Box 2 or somewhere else in your book of truth, right? If I take a triangle, and this time I don't make a median, but I go from A, and where I intersect, I make a right angle. Like I move this red around until it reads 90 degrees. See what I'm doing? I'm going to move it here. Oh, that's not 90. Move it. Oh, that's 90. If you make a 90-degree angle, that construction red there, we don't call it a median. We call it an altitude. So an altitude You go from a vertex to the opposite side, but the angle that's formed is 90 degrees. Now, it's hard to, I chose the first one they used in the book. It's hard to see here. Does it look like it cuts it in half? Like, does it look like it cuts BC in half here? Sometimes it can, but most of the time it doesn't cut it in half. Notice if I make the altitude from B, clearly it doesn't cut AC in half. If I go from C, clearly it doesn't cut AB in half. So it's not that altitudes can't cut the opposite side in half, it's just that usually they don't. So medians do cut the opposite side in half. Altitudes are just altitudes. All right, let's see who remembers it from pre-algebra. What's the formula for area of a triangle? Times height. Altitude is another word for height. And if you had me for pre-algebra, I made that point. I said that eventually we're going to start calling this an altitude. If you remember all the pictures we had when we were doing area of a triangle, they all had a little tiny square on it for the height of the triangle. And I said, I wish they would call it the altitude, because that's what we're going to call it in 3 years from now or 2 years from now when we take geometry. So that's what an altitude is. If that were it, once again, just a median and an altitude, it would be pretty easy to remember. The issue is we get lots of things from this basic concept, both median and altitude. Oh, by the way, what type of triangles are all three of these? Maybe, but they're certainly acute, right? So I drew acute triangles for both my medians and my altitudes. The question is, what would altitudes look like if it wasn't acute? Okay, the big but here is that, well, what would an altitude look like for a right triangle? What's the requirement to make an altitude?
Right angle.
So what would an altitude of a right triangle look like? It would be part of the triangle, right? In other words, the side, the leg of this right triangle is the altitude. But wait a minute, what's this? Another leg, and it makes one. So the other one is also an altitude, but wait a minute. There would be another one. Where would that one go? That would go through D, through EF, and it wouldn't be a side. So one of the altitudes of a right triangle, in fact, it's the side that is the hypotenuse, kind of looks like an altitude. The other two end up being sides. This is why when you did, if you remember back to pre-algebra, when you did an area of a triangle and it was a right triangle, you just basically multiplied the two legs together and took half. Okay, the base times the height. Okay. Okay, that's it for right triangles. We got one more triangle left. We did it for acute. We did it for right. Obtuse are weird. You might have remembered this from pre-algebra. This is a really big but, right? I should have made it twice the size. When you have obtuse triangles, right? Well, there's an obtuse triangle. I got to go from L to what? To make an altitude. I got to go from L to the opposite side. Is there any way to make a right triangle if I go from L to the opposite side? There's no way to do it. I can't get, can you see the problem here? If I try to draw from L to KN, you'll never make a right triangle. Do you remember how you solved this in pre-algebra? I mean, you did the area of an obtuse triangle. Do what? It sort of visually looked like that. That's not what I'm doing, though. Anybody remember in pre-algebra what we did? You take the side and you extend it, right? You remember extending it like that? You put the little dotted line right there, and then you drop it straight down. So even though that's the measurement correctly, this part, this is why a lot of kids think it's two triangles. It's not really two triangles. This red and this dashed are just auxiliary lines. Okay? So it's going to look weird, right? Here is the actual triangle. If I go from N to the opposite side, I'd never get a right triangle, so I have to extend it. One of the sides will be okay for obtuse, just like it is for right. But the other two sides will look weird. So we did medians, go to the middle, altitudes, 90 degrees. So far, we haven't had anything we can calculate yet, right? All right, so what just happened, right? The definitions, median goes to the middle, right? Cuts the opposite side in half. Altitudes don't do anything other than make 90-degree angles. That's it. We get nothing from that until we get to area, and then we actually use that. Okay. All right. Cool. That's pretty easy. All right. More definitions. All right. Well, clearly that's not a triangle. That's a segment, right? So if I find the middle of that segment, I've just made what? Two more parts, right? So that's congruent to that. Yes. Okay. If I make another segment that goes through this unnamed red point right here, and I make it perpendicular, see the red line I just made? If I make it perpendicular, what do we name this red line or segment array then? If this red line or segment is perpendicular and it cuts the other segment in half, what do we call the red part?
Perpendicular midline.
Close, but no cigar, but really close. We call it the perpendicular bisector. So write that one down. And we have talked about this before. A perpendicular, it can be a line, array, or a segment. So even though it's called perpendicular bisector, it can be any one of those shapes. But it's got to be something that cuts the other segment in half. You can't have a perpendicular bisector of a line, because you can't cut a line in half. It's infinite. But you can have a perpendicular bisector of a segment. And the thing that cuts it in half could be a line, array, or another segment. But it's got to cut the other segment in half, and it also has to make a right angle. We call that a perpendicular bisector. It's a line, array, or segment that is perpendicular to a segment at its midpoint. It doesn't say cut in half, but that's the consequence of it, of being a midpoint. My square is really poorly drawn. I apologize. All my squares today for show something that's perpendicular are really off. I couldn't get PowerPoint to cooperate. There is a computer program that I use occasionally that can draw it perfectly, but it takes some time to make it happen. As more years I teach it using this book, then my pictures get better. All right, we good? So let's see. Median cuts things in half. Altitudes make right angles for triangles. And a perpendicular bisector cuts the segment in half, and it forms a right angle. All right. We've got to do at least one proof today. All right, here we go. This one's actually pretty easy. There's a lot of words there. All right, let's focus on what it's asking us to prove. What's it asking us to prove? What's it asking us to prove? So A, B are the red parts right here. So I'm trying to prove this and that. All right, you're on. Take a look at the shape. What do we got? No. Take a look at this more general. He's already trying to give me the answers. Even more general that. Look at the shape. What do we got? I got two right triangles. So it's asking us to show what? That two parts of are, no, it says equal this time. It doesn't say congruent. Oh, what? So even though that's my start and that's my finish, this will be number 13. Well, how do you show that two parts are equal?
The same way you show that.
The same way that you show that they're congruent. So I already know what the previous step is. I'm going to show that the two parts are congruent. Further, Bailey, how do almost all proofs end that showing two parts are congruent? Number 13. If I show two parts are congruent, how do we do that? 3 steps. 3 steps. Step number 1. This is number 13. Show that they're are A, B, and B, C part of two different triangles, Bailey, yay or nay? Okay, step 2. So we're going to show that the two triangles are congruent, and in step 3, we're going to, so I can already write it right here. I mean, I already know how it's going to end. It's going to end with, well, that's definition of congruence, and it's going to end with CP/CTC. I could already write that down if I chose to. I know how the story ends. And Wes has already got it proven. At least I think he has. Okay. Better, Bailey, today than yesterday. Okay. So now the rest of you guys are on. We got to get to the two triangles are congruent. Well, we know that they're a perpendicular bisector. These blue marks, that was already there, so I got to state that though. So I know that BX is congruent to CX. Why? Because, well, that's the definition of a bisector. Something cut something in half. Okay, so I got an S. What else do I need? I'm not lying when I said Wes already got the darn thing solved. I got an S. Remember, it's either SSS, SAS, AAS, hypotenuse leg. Hey, it's a right triangle. Maybe it's hypotenuse leg. Yeah. Why would it be SAS? That's what Wes said too. Well, we got another S right here. You see the two triangles? They both share side AX. So we got AX is reflexive. We need an A. If you want to use SAS, where's the A come from? What do you mean about the angle? So therefore, each angle is 90. You see that? If it's perpendicular, it means this angle here, BXA and CXA are both 90. So there's my A. There's your reflexive. Let me catch up with you. We good? And then she said, wait a minute. Well, it's a perpendicular bisector. Therefore, those two angles are 90. So do we have SAS now? We do. And we're done with the proof. And Wes did the whole thing in his head. I'm just going to say, some people, you catch on at different levels, right? Some people, all of a sudden, it starts to really click. I mean, really click. Right? Other people, it just takes time. Right? CP, CTC, and you're done. What the heck did we just prove? It said that we started with line L, and it's a perpendicular bisector, and it said you had a point on the perpendicular bisector. What did we just prove? That if you're on a point on a perpendicular bisector, that what? That this equals this. Well, what are those two red lines? It's a hypotenuse of a right triangle, sure. Absolutely 100% true. They're going to give it to you in more general terms. This is the hard one to wrap your head around. Let me try to draw a picture for you. So this is Theorem 4.5. It says this. If you start with a segment, right, you with me? And you make a perpendicular bisector of that segment. So I'm going to make a perpendicular bisector. It says the following. Pick any point on that perpendicular bisector. Literally any point. Doesn't matter. I'm going to pick this one. This is what Theorem 4.5 says. It says that if you live on this perpendicular, by the way, it goes down here as well too. If you live on the perpendicular bisector and you were to draw to the endpoints, what can you say about the two black dotted lines? That they're congruent. They have the same measurements. There's going to be a lot of words. This is what the theorem means. If you live on a perpendicular bisector of a segment, you are equidistant to the two endpoints of the segment. I'll say that one more time. That's what the proof's going to, or that's what the theorem's going to say. If you live any point along here, we're not saying that any point has the same distance, right? Those four black lines are not congruent, but the pairs of black dotted lines are congruent. Does that make sense? Okay. That's Theorem 4.5. Write that one down. It says, if a point lies on a perpendicular bisector of a segment, then that point is equidistant to the two endpoints. It just means it's the same distance away. In other words, if you were to connect the dots there from A to B and A to C, you'd have made, right, two triangles where the hypotenuse are equal. That's actually what you're going to use this particular theorem for. Hey, the hypotenuses are equal. Therefore, you got a hypotenuse leg. There are congruent. The triangles are congruent. So that's generally when this proof is used, this theorem is used, is when you're trying to prove that two right triangles are congruent to each other. Theorem 4.5, a point lies on the perpendicular bisector of a segment, then the point is equidistant from the endpoints of the segments. In other words, the distance from A to B is the same as from A to C. If there is a skill involved, they're going to say that AB is 10, therefore AC is also 10. It's not much of a skill, right? Cool? All right, we do have the converse of this. So the converse would be this. You're going to prove this one tonight for homework. The converse would be if A is equidistant to B and C, then it must live on the perpendicular bisector. So it's the same statement, just the converse. So if A is, they're going to give you the fact that A is the same distance from B and C. Therefore, it must live in one place only. It must live on that perpendicular bisector. That's the converse. And by the way, I've already told you how to prove it. Or we already got a hypotenuse. Maybe we can get oh wait, we have a leg because look, it's reflexive. Done. And I just gave you the answer for tonight's homework for the proof. You see it? Hypotenuse, reflexive for the leg, HL, done. Therefore, that's congruent to that. Therefore, the two measurements equal each other. Therefore, this angle is congruent to this angle. Therefore, they're both 90. Easy, 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 if you pay attention. Good? Okay. All right, so what just happened, we talked about theorem 4, 5, 4, 6. It's a biconditional statement, so it's an if and only if, but they break it down into two separate ones. So theorem 4, 5 says, if you have a point on the perpendicular bisector, right, anywhere on the perpendicular bisector, then those two black lines that I'm drawing right here, right, those are congruent, okay? Theorem 4, 6 says the converse to that. It says that if a point is equidistant to the endpoints of a segment, then that red point must live on the perpendicular bisector, if and only if. Okay. Next idea. Another definition. This one's a little bit easier. Hey, what's that? What's that? How do we measure the distance from the point to the line? Oh, silence. How do we measure the distance from the point to the line? On your ruler. Okay, got a ruler. Now what? Okay, put it on the dot, and then put it on the line. It looks to be about 15 centimeters. Yes? You agree? That point is 15 centimeters away from the line. Why do you disagree? Well, yeah, but I did what she said. I measured from there to there. Literally, does this not say 15?
Yeah.
If I were to turn it, oh wait, I am getting different numbers. So how do you measure from a point to a line? We got to use better words than straight down. We got to make a right angle. Do you agree? If we don't make a right angle, we're going to get a different number depending upon who measures it. But if you make a right angle, you get 1. What's so special about a right angle? And this particular geometry. True.
And
this is part of everyday human speech. There's a saying about this, by the way. The shortest
distance between every 2 points is a straight line.
That's what we say. It comes from this right here. The shortest distance between a point and a line is a right angle, right? So this is called the distance of a point to a line. It's only ever measured perpendicularly. I hate saying that word, perpendicularly. Try to say it too fast. We always measure the distance between a point and a line perpendicularly. If we don't, yeah, it is. If we don't, then we get different numbers. If you measure it perpendicularly, then it's the shortest distance. That's a pretty easy concept. But we have to make it. Otherwise, people would be measuring things strangely. We also, It's not necessarily in the statement, but it can't be measured with a curve either. It's got to be a straight. It's got to be a line, right? Measure with a curve, then we absolutely induce more distance
And headache.
potentially, especially if you're building something, right? We good? All right. Hey, I started off by saying this. I said that I'm going to show you two basic theorems. You're like, well, you already did. Well, I technically showed you one. It's just biconditional. And I said it's just like the segment addition postulate and the angle addition postulate. I'm going to show you something that also applies to angle. Here's the same something, except it's angles. It's the same idea as that previous proofs that we just did. Okay? It says that you have an angle bisector. Danny, what's special about angle bisectors? And it into that are perfect. Well stated. All right. See the little two blue marks, right? So BZ is an angle bisector, cuts things in half. Okay. Okay. We're trying to prove that PX red is congruent to PY. It's the same proof. Hey, PX and PY are part of two different triangles. I got my given, right? How do we show that two things are equal? Show that they're congruent. I already know how this ends. What's the reason? And then the next statement will be definition of congruence. I already know that's how it ends. Okay. We got reflexive, yes. Are the two triangles congruent? Look at it. What's marked there? Angle, angle. I should go angle, angle, side. So therefore, the two triangles are congruent. I do need to say that this is wrong. It's not definition of perpendicular. Definition of bisector. I should say bisector right there. Darn it. You know why it says perpendicular? Because I copied it from the previous proof. It's the same proof. It's just for angles. So this should say bisector. All right. So the in fact, that line shouldn't even be there. BXP. Oh no, that's good. That's good. Take back everything I just said. That's right. I do need to say that because I need to say that this angle is. Yeah, that's right. That's right. All right. Two triangles congruent because of angle, angle, side. And then therefore the two parts by CP/CTC. So let's see. If you live on a perpendicular bisector, you're equidistant to the side. If you live on an angle bisector, you are. If you live anywhere on the angle bisector, what do we just prove? That you are equidistant to the two sides. That's what Theorem 4.7 says. That if you live anywhere on the angle bisector, anywhere, P or Z, that you are the same distance away from the sides. And the reason why we measure it perpendicular, because of the previous statement. That's how we measure things. How far are you away from the line? You measure perpendicularly. This is 4.7. If we have 4.7, guess what we would also probably have? And 4.8 is going to be the converse to this. If you are equidistant to the sides of the angle, you live on the angle bisector. I'll write that here in a second. I think we got what, a minute or two left? No. We made it. I made it with 2 minutes to go. I was worried I wasn't going to get through this class. I'm not sure why. This summer when I was looking over this, I identified this as one of the ones like, oh, I'll never get through this one. All right, let's write down the converse. You will prove this one to homework. Hey, who can prove this right now? It says if PX is congruent to PY, why does it live on the angle bisector? We got a what? We got a what? We got a hypotenuse and we got a leg. It's hypotenuse leg. It's the same proof of the converse. So you're going to have an HL, therefore that CP, that this angle is converted to this angle, and you're done. There's the proof. If you remembered it, then your homework's easier. Converse is, I think that's why they have you prove the other one in class, is because the converse is easy to prove. The other one's a little bit more challenging. Not too hard, though. Cool? They're not all proofs tonight for homework. This was a lot of stuff, though, I will say. You need to digest this stuff, right? For homework questions 1 through 6, open up your books real quick. Just look at 1 through 6 in case there's any questions. No, but I'm saying look at 1 through 6 first to explain what's going on here. What page is it?
It's page 56.
One what?
56.
So if we look at 1 through 6, it's asking you to draw triangles, right? Draw. It will take you some time. Okay. You're going to get to these questions. It's going to say to draw the 3 things. And it's going to ask you something. It's going to say, what do you notice? You're going to notice that the intersection points happen physically somewhere. Inside the triangle, on the triangle, outside the triangle, right? That's all they're looking. We'll actually use that in chapter 10. So I'm not sure why they have you do it now. It would seem like a better fit for chapter 10, but they had to do that now. You're going to absolutely forget it. I'll have to remind you. All right, have a good 3-day weekend. I know I will. All right, e-learners, if you have any questions, let me know. If not, you guys have a great 3-day weekend.